Yes, class. Sarah, you didn't join the previous class. Alia was there. Harsha was there. Thermal properties of matter. You don't want to study, Sarah? See, I won't be giving any backup class for that. Let me be very clear, and I have mentioned this earlier also. That is not something extra I'm taking for your upcoming exams or something. That is your regular normal class going on. The way you have this batch, there 1 hour extra time we have calculated from your regular batches so that your thermal unit can be started simultaneously. So that here we do not have to rush up. Slowly fluids will be completed. Slowly your waves and oscillations will directly be started here. And there your thermal unit will be going. So your syllabus will be on time. That's why it has been started. Any particular reason, Sarah, or not?
Mom, I left my iPad at school.
Hmm?
I left my tab at school. The one I take classes from.
You left your tab at school.
Yeah.
So there was no device left for attending the class.
There's no other number in which Learnivio's number is.
Okay, please see the recordings then. If you have
I
any
saw.
doubts on the recordings, then let me know. Doubts will be clarified then. Yes, now we stopped at this point, terminal velocity. Terminal velocity is basically if a body is going, initially the velocity will increase up to a certain value. Then the velocity will become constant. And that constant velocity is known as terminal velocity. Why? Because the buoyant force and the mainly your buoyant force and your Stokes law. These are the two quantities that come into action. What was Stokes law? Stokes law gave you the viscous force into action. So viscous force and buoyant force. Mainly combination of your Stokes law and your buoyancy. So buoyant force and Stokes law, buoyant force and viscous force, they balance your weight. This is the concept which we have studied. So we have practiced numericals are left. We'll see this. Before we start with this, you have to understand that if the density of the body is greater than density of the liquid, suppose this is flowing, a body is coming down and the density of this body is greater. See, in this formula, what was the formula of terminal velocity? 2r square g rho minus sigma divided by 9 eta. Right? This was the formula. So if rho minus sigma, if rho is greater, so rho minus sigma will be positive. If rho minus sigma is positive, terminal velocity will also be positive. So if terminal velocity is positive, downwards is supporting, so body will move downwards. Body will move downwards. If vice versa occurs, suppose let's say the density of the liquid is greater. So here what will happen? Rho minus sigma, this will be negative because the second number is greater, first number is lesser. It's like 1 minus 3 like this. So this will be negative. So terminal velocity will also be negative. So in this case, what will happen? Body will move upwards. Best example you can say, when a air bubble is there at a depth in the bucket, you see the air bubble coming up. Why is it able to come up? If the terminal velocity acts downwards, if it pushes it back. No. It means the density of the liquid is greater than air. Liquid density of water is greater than density of air. So air bubble comes at the surface because the direction of terminal velocity reverses because of the reversal of densities. Now we'll see a question. Write this down first, then I'll discuss the question then. Yes, Martin, where were you? Right now you are joining the class. First class you were there. On Saturday, I think you have attended the class also when we started the unit heat. You were there in the class. Yes, Martin.
Yeah, ma'am.
So, why didn't you attend the class today, Martin?
What, ma'am?
Thermal
There was
class,
class.
thermal properties of matter.
There was class today at 6:30.
You had a class today at 6:30?
Oh,
So
sorry, ma'am. I didn't know.
we had the class between 8 to 9. 6:30 to 8 you have your classes. So we had the classes between 8 to 9. That time I don't think so you have any class. Please check the schedule, Martin, properly. Let me know if anything is clashing. This is 100 meter per second. This question says a water drop is in air has terminal velocity 100 meter per second. So 8 drops are there. They have combined and formed a bigger drop. So one thing for sure that will remain same is that their volume. If you have 8 drops and you have combined the 8 drops, ultimately volume is same. Whatever is the volume of that total of those total 8 drops is the single volume of that one bigger drop. So let us first find out the relationship between the radius of it. So volume of 8 drops is equal to volume of that one big drop. So how do you write the volume of 8 drops? 4 by 3 pi small r cube. Small r I am referring to the smaller sphere. So 8 times that is equal to volume of one big drop, that is 4 by 3 pi capital R cube. Correct, class? So take the cube root, 2 times small r is equal to capital R. This is one relation. Why do we need it? You will see. Class, tell me one thing. In this entire calculation, right now, in this question, what all things are necessary? What all things do we need in this question, in this particular question? What all things do we need? 2 is a constant. Okay? 2 is a constant. 9 is a constant. Coefficient of viscosity is a constant. Eta, this is constant. Acceleration due to gravity is constant. The fluid is the same, right? Both the fluid before and after, it is the same. Those same water droplets have combined. So density here is also constant. Radius is changing. It was initially small r for the smaller droplets. It is now capital R for the bigger droplets. So capital R and small r. If you take the ratio between the small drops and the bigger drop, between the terminal velocities, do we need to write everything? Can you notice that everything will be cancelled? 2 by 9 g rho minus sigma eta, these will be cancelled. Only will terminal velocity and radius will not be cancelled, because obviously we have seen radius is changing. So terminal velocity is directly proportional to r square. Directly write it. Why to write everything and then cancel 2 by 9, 2 by 9 and then show cancellation of acceleration due to gravity, acceleration due to gravity. So velocity, terminal velocity of the smaller drop is equal to r small r square divided by terminal velocity of the bigger drop is equal to capital R square. We know the relation small r square and capital R square. Capital R square is 2r. So that will become 4 small r square. This will be cancelled. What are we given? Water drop in air has terminal velocity. So basically, water drop has 100 meter per second is given. No, it will be 400 meter per second. Capital R will be 4 times the velocity of the smaller one, which will be equal to 400 meter per second. That's it. Easier way you can perform this question. Write it down. Yes, class. Now the types of fluid flow. Fluid flow, you have equation of continuity, you have that we have to discuss. So there are certain assumptions that you have to assume before we are discussing the fluid. See, every fluid cannot be ideal, but there are certain characteristics of every fluid. So first is that we assume that there is very less viscous force acting between the adjacent layers. It means the motion of the fluid is very smooth. Though in reality, we know that every time between the layers, there will be a viscous force acting in the backward direction, in the opposite direction to the flow of motion to provide internal friction between the adjacent layers of fluid. But when you are assuming something to be ideal, you ignore the reality, real consequences which are possible. So the fluid is non-viscous. This is the first thing. Means there is no internal friction between the adjacent layers of the fluid. Secondly, fluid is incompressible. Incompressible means density of fluid is constant. Volume, mass, density, nothing is changing. Volume is also fixed. Mass is also fixed. So density of the fluid is fixed. And fluid motion is steady. When I say the fluid motion is steady, this means that we'll see. Steady flow, let me tell you. This steady flow, let me be clear with this. The types of liquid flow. The steady flow, which I was mentioning, there is one more term to it, which is known as the streamline flow. What is meant by a streamline flow? Now pay attention to it. The flow of a liquid is said to be streamline flow or a steady flow if all the liquid particles that pass at a given point follow the same path and the same speed. See, suppose many particles are coming. This is a path of flow of some liquids. I am emphasizing on this point. Suppose this is A point. When a particle came here, its velocity here was 3 meters per second. When it came, its velocity was 3 meters per second. Then I note this moved away, and here its velocity at B point, this became 2 meters per second. And at this point, at this C point, this velocity became, let's say, 2.5 meters per second. So this is one particle which is moving. Then what am I noticing is that the second particle which is coming, which was already here, the second particle which was already there, when this came at this point only, the motion could have been that this particle could have been over here, this point. It could have been over here. It could have been over here. The path would have changed, right? It's a fluid flow. But no, whatever was the path of the successor, it will follow it. Fine. The path of the successor will follow the path of the predecessor. It means this is coming. A already came with this velocity at this position. So second particle will also come at this position only with the same velocity. Now this particle moved from A to B, came to point B a little lower with velocity 2 meters per second. So the molecule which was following it, that will also come a little lower and come at point B and have the velocity 2 meters per second. So this pattern, this creates a pattern flow because every particle is following one another, which is moving. So we call this type of pattern as streamline flow or the steady flow. Second flow is known as laminar flow. Laminar flow, we say it's a type, special type of streamline flow only, but there's a difference. Here, it is a special case of streamline or steady flow in which the liquid flows as a series of parallel layers, that is laminar. The word laminar is only because of it. Like this, smooth, straight path, like this. Like this. None of the layers are overlapping each other. Smooth streamline flow. Streamline flow could be curved, right? Because at a point it can happen. The layers do not cross each other. Turbulent flow. Turbulent flow, they can cross each other. Fine. Disorderly, disorganized flow, like this. Liquid flow at a point is like this, and at a point is like this. This kind of pattern, where there is no pattern of flow of fluid, like this. This is known as turbulent flow. direction is changing, speed is changing, the orientation of the molecules are changing. So turbulent flow is the flow of liquid is said to be turbulent, or disorderly flow. Disorderly word can also be mentioned if the speed and direction of the liquid particles passing any point change with time. See, this particle is not following it. All this is changing with respect to time. All right. Next is rate of flow. See, rate of flow means the amount of fluid that crosses per unit area. Rate of flow, how much amount of fluid has flowed. So volume of liquid that passes a cross section. Suppose this is the end of a pipe. So whatever is the volume that is coming, volume of the fluid which is crossing this. So volume per unit area. This is called rate of flow. Amount of fluid which is crossing per unit cross-sectional area. This is known as the rate of flow. We will be using rate of flow in equation of continuity. First, write down all this. We'll see some parameters, Reynolds number. Some numbers are there. Reynolds number is there. You have critical velocity, small parameters. Then we'll come back to the usage of volume, rate of volume, rate of flow in the section of equation of continuity. For the time being, write down this. Yes, class. The next topic is Reynolds number. So now how will you determine whether the flow of fluid is turbulent, laminar, or streamlined? See, this is given by a mathematical parameter. Certain range will be there. Whatever the number will come, you will calculate whether it's laminar or turbulent. There's a formula for calculation of Reynolds number. See, rho is the density of liquid. So rho, V is the velocity of liquid, D is the diameter of the pipe divided by eta. What is eta? Eta is coefficient of viscosity. This is coefficient of viscosity. Now see, if you are getting the value less than 1000 or maximum equal to 1000, like 999, this also 840, any number, that will give you either streamline or laminar. Means it is laminar or streamline. Both are actually same. It's a modification only. If it is greater than 2000, then it's turbulent. But see, in between 1000 and 2000, there is a possibility that you can get a value between 1000 and 2000. Less than 1000, you will say it's streamline or laminar. More than 2000, you will say turbulent. But what about between these two? It means it is not fixed. It is not one single streamline or one single turbulent. It means it is continuously shifting between turbulent and streamline. It is continuously shifting between turbulent and streamline. All right, this is what is meant by Reynolds number, continuously shifting. One more topic is there, critical velocity. See, there is a point, there's a velocity. If that velocity is there, the flow is streamline or laminar, you can say. When that velocity, maximum velocity is reached, after this velocity, the fluid will become turbulent. So that maximum velocity, till the time the object, the fluid flow is steady, that is laminar or steady, streamline, we call it as critical velocity. So critical velocity, there is a constant. We write the constant here. This will be given to you. Eta, coefficient of viscosity, density of the liquid. This is not density of the body, density of liquid, and D is the diameter. Let me write down all the parameters. This is the critical velocity. This is coefficient of viscosity. Coefficient of viscosity. This is diameter. This is density of the liquid. Diameter of pipe. This is density of the liquid. Now see, if the flow, if the velocity of the fluid, this is still less than the critical velocity, whatever is the value, it will be streamline only. But if the velocity of the fluid exceeds this critical velocity, it will in any ways become turbulent. So these are the two criteria. How can you identify both of them? Let's see numericals also on them. First, you copy it down. So these are the two methods by which you can identify what is the fluid flow. Write it down. This question says the flow rate of water from a tap of diameter 1.25 centimeter. This is 0.48 liters per minute. Coefficient of viscosity is 10 to the power minus 3. After some time, the flow rate increases to 3 liters per minute. So we have to find out, we have to characterize it. Means we have to find out the type of flow. Rate of flow, this
What
is
is written
point.
after 10 to the power minus 3?
That's the unit given, Pascal seconds for eta, coefficient of viscosity. Or you can even write deca, boys, but in this question it's given Pascal second. So 0.48 liters per minute. So we have to convert it. 0.48. This becomes into 10 to the power minus 3 for meter cube. And 1 meter will become 60 seconds. So this is 0.08 into 10 to the power minus 4 meter cube per second. This is the initial. Eta is given as 10 to the power minus 3 Pascal seconds. And what is the final one? This is increases to 3 liters per minute. So it would be 3 into 10 to the power minus 3 by 60 seconds, which is 0.5 into, this will increase 10 to the power minus 4 meter cube per second. Now we have to characterize the rate of flow.
Ma'am, what is Q?
Q is rate of flow.
Okay.
This is rate of flow of fluid. You represent it by the symbol Q. And let me tell you this. Rate of flow, Q is equal to volume per unit time. Volume is written as area into length. T is the time. So length by time. What is length by time? Which quantity is this?
Velocity.
Velocity. So rate of flow is area into velocity. All right, this is area into velocity. So if it's a circular end, you will say it's pi r square into v. Here diameter is given, so we will write d square by 4 because radius is half of diameter into velocity. This will give you the rate of fluid. So you will calculate Reynolds number. In this question, calculate Reynolds number. What all values are given? See, Reynolds number is this, rho Vd by eta. So density, this is water, that's 1000. Okay, this 4 will go up. So this will become 4 into 1000. Velocity 0.08 into 10 to the power minus 4. See, pi is there. So that becomes 3.14 10 to the power minus 3. And we have 1.25 into 10 to the power minus 3. This was for time. So this, when you will calculate, this will come out to be 815. Just check the calculations once again. This is less than 1000. So you can say this flow is streamline. All right, this flow is streamline, initial flow. Then you will calculate the same thing for the final one. Same thing. Reynolds number for the final
Flow
one.
is not there in the formula, right?
Hmm?
Rate of flow is not there in the formula, right? For
No,
Reynolds
rate
number.
of flow is not. Rate of flow is not. Rate of flow is giving you the velocity. Rate of flow, no, this is giving you the velocity. Velocity of the fluid we require. That's rate of flow is not there in the formula. So similarly for the second one also, second velocity you will put it as 0.5 into 10 to the power minus. So you will get some value. Just check whatever values you're getting. Let me know. I think the second one will come out to be 5096, which will define turbulent flow. Acha, Harsha, what you're asking, I understood. You're asking why are we writing rate when velocity is mentioned? Velocity of liquid. See, what is velocity? Velocity is distance covered per unit time. Here in rate of flow. Rate of flow of fluid is actually the velocity of fluid only. Rate of flow of, if I say rate of change in distance, that we say it's velocity, right? So here, what is the distance covered? Whichever volume is being occupied by the fluid, how much volume is the fluid occupying, divided by time gives you the rate. So fluid flow is like distance. Fluid flow is giving you the distance. How much fluid has flown? That is telling you the distance covered by the fluid. By the time divided by time is giving you flow of fluid by time. So something divided by time is known as rate of flow of fluid. But in reality, what it is? It's the velocity only. Understood? This is like velocity for fluids. Is it clear, Harsha?
Yes, ma'am. Ma'am, why is 1.25 in the denominator?
Diameter 1.25 centimeter.
Ma'am, but in the formula it's rho V D, right?
D is the diameter only, no?
Yeah, ma'am, so it's in the numerator, right?
Rho V T, yes. Should come in the numerator. See, if we convert it, 10 to the power minus 3 Reynolds number. Yeah, it would be in the numerator then. Yes, yes. So rho V D, D is the denominator. I have written it in the denominator, no?
And
Coefficient of
ma'am, why
viscosity,
is
rho V.
pi in the...
Hmm?
Okay, yeah, I got it.
Yes, yes. Right, right. Just check the calculation also. Let me know what's the answer.
Okay.
The equation of continuity says what? This is, suppose I have taken an irregular shaped tube. Here area is lesser. Fine, area is less. Velocity is V1. This is A2, this is V2. So initial velocity is V1 at end 1, at the end 1. Velocity is V2 at end 2. Now, for streamlined flow of an ideal fluid, ideal motion, the rate of fluid is constant. Fine, ideal fluid, the rate of fluid is constant. So Q1 is equal to A into V. Well, basically, your rate of flow is constant, A into V. So because whatever mass is entering is equal to mass leaving. So you can say A1 V1 is equal to A2 V2. That's it. So this equation you can use. This equation will be helpful in many cases. In Bernoulli's theorem, we'll see in the next class also. This equation will be used. Though I have told you also, but equation of continuity separately can also come. That's why write it separately. A into V is equal to A into V. Whether the ends are irregular or regular. Write it down. Regular also we'll see a special case, but that also that all we'll discuss in Bernoulli's. If you all have completed, you can start leaving. In the next class, we'll start with Bernoulli's theorem on Thursday. Okay. Thank you so much.
Okay, thank you, ma'am.